Yeah, thank you, everyone. I'm happy to be able to present, especially remote. I wouldn't be able to make it otherwise. So thank you for having us. Now, my name is Cameron Gibbs. I'm a knowledge engineer with Crown Point Technologies, and I've been supporting the Pistoia Alliance in the development of a different ontology. This is their CMC process ontology. The Pistoia Alliance has been really driving and organizing this group to develop the ontology. We have currently in this initial phase, we have 3 sponsors that are also steering it as well, from Amgen, Johnson & Johnson, and MSD. And I think together that it's been our initial phase has been very fruitful. I think I'm happy with the output, and there's been really great direction and output from everybody. Hopefully, all the other members feel the same. But this is an early stage ontology. So unlike the IDMP, we've only been working 6 months now. We're wrapping up our initial phase. But we felt that this was a good opportunity to bring some of our work out to the broader community, especially because there is overlap in the content, the domains that we're working with. But although there is also, I think, some different use cases between what we're focusing on and what AFO traditionally focuses on. And I think that might be an interesting area of connection. So the primary objective for this project is building a pharmaceutical CMC process ontology. We're incorporating aspects of the ISA 88 and 95 framework to standardize lab and plant production process recipes. I should say we're incorporating aspects of those standards as they become needed for use cases and supported by sample data. I'm sure as many people are well aware, you can use standards at different organizations, but how they're used itself is not always standardized. So we want to take great care in how they're incorporated into the ontology to really help standardize the use of these definitions and support interoperability. So we are incorporating aspects of these standards in terms of process definition, in terms of process location, site location, and so on, as they're needed by the use cases. The main goal is really to establish standardized definitions that are going to facilitate things like digital technology transfer. Is really the ability to take a pharmaceutical manufacturing process that has been done at the smaller scale, at the laboratory scale, using small volume equipment, and being able to scale that up at a production level, making it cost efficient, making the yield high, and so on. This is really one of the core issues surrounding the general process domain that we want to support, and then integrating this with the execution systems that are ultimately going to control these manufacturing processes. Our inputs are going to be structured process data for things like material genealogy tracking, the process data that goes into technology transfer, so comparing things like the measurements on the parameters that were set in that manufacturing process and comparing those with the recipe limits that were specified in a recipe, as well as the advanced process analytics, some amount of analytic measurements taken on samples from these manufacturing processes and being able to compare them across different batch processes. All right, so the plan is I wanted to give not only this quick overview and a discussion of some of the use cases and the business value of the ontology, then a little discussion at a high level about how the ontology works, some of our modeling decisions, and a proposal for how it integrates, or potential integration point with the Allotrope Foundation ontologies. And then finally, a little bit of some of the results that we had from a prototype that we built. All right, so these are some initial use cases that drove our development. The first 3 are really the core we focused on in our project. The fourth is something that was kind of incorporated based on material that was already built into some of the ontologies we imported from the IOF, the industrial foundry ontologies. And there are certainly some future use cases we're focusing on. But to begin, so the first use case, the really foundational one, is process definition, the ability to define a process in a fully standardized way that can be both site independent and site dependent. Also, not listed here, equipment dependent versus equipment independent, being able to have standardized ways of defining that manufacturing process. Here is we really have incorporated the ISA 88 terminology, so the distinction between different types of recipes, like a general recipe that's completely independent of equipment or of the site, down to site-specific recipes and equipment-specific recipes. We've also incorporated that standards breakdown of the different process steps from for example, a process being the highest level of a step governing a manufacturing process. The process itself is composed of process stages, which are composed of process operations, which are composed of process actions. So the ability to standardize on these manufacturing processes is a real need as we're comparing across different sites or different runs, for example, ensuring that all users are talking about the same step in the process, they're talking about the same recipe in the same sense, whether it's site dependent or independent, is a really foundational use case for our development and is a huge need in this domain. Now, building on top of that, we're coming to process monitoring. Here is using the fact that we have a standardized way of defining a process, we can now aggregate and track measurements taken throughout that manufacturing process, which could be done using different sensors, and there could be different data systems collecting these measurements. But with the standardized process definition, we can collect them through that manufacturing run. We can, for example, have an end-to-end temperature profile, and also importantly, be able to compare that profile with the limits set for it by the recipe. So for example, typically something like temperature, there's going to be limits, the upper and lower limits for where the temperature should be in the manufacturing run. Being able to easily identify if the temperature profile goes out of those limits is going to require aggregating across this process, needing a standardized way of defining the process and a standardized way of defining the measurements and the recipe requirements listed. Okay, and then building on top of that, we come to comparative analysis. So now we're moving beyond aggregating values within a single manufacturing process to now aggregating across different batch processes. So we might not only would we be aggregating and comparing measurement values between different runs done on the same machinery, but cross scale. So there would be different equipment being used, different sensors being used, different personnel involved, and even different cross site where there's going to be even more differences. Data collection techniques could be different, schemas could be different, data systems would be different. So this is where the full power of the ontology is going to come in, and by having a standardized framework for defining this process that can be used across any recipe, across any site, across any equipment, we can make these comparisons. And this is really crucial for engaging in things like the tech transfer analysis, where we need to be able to compare how are things like the pH levels comparing at the lab experimental level with other scales or at other sites where we're at the production level, to make sure that we're getting the highest purity, the best yields, the most efficient process, and so on. Now, like I mentioned, the first three are our core use cases driving development. The fourth, so raw material impact, this is something really coming from the IOF ontologies that we've incorporated. They have pretty extensive modeling for the raw materials that would be used in a manufacturing process. And we have, with our work in defining a standardized process and standardized measurement and analytics values, can extend that raw material analysis that they've provided to be able to track the point in the process at which the raw material was used, and seeing its impact on different measurement values after the fact. So this is also something involved in it, but wasn't really driving our main development. And then finally, there are certainly many future use cases we want to explore in future phases of the project, including supply chain considerations. I think would be greatly of interest to the group. This could be an interesting integration point with the IDMP ontology. There are many other aspects of tech transfer we can incorporate going further, as well as quality investigations and compliance and reporting. All right. So I wanted to spend a little bit of time thinking about, given a standardized model that the ontology provides that gives semantic interoperability, I think it would be helpful to think about from at a high level how that ontology can be used to provide business value. This is kind of I think a good bridge from the previous talk about implementation. But I wanted to have a kind of conceptual idea of how we could implement the ontology before digging into some of the modeling decisions we made. So here is just a very basic breakdown of what is often typical in the current state of digital manufacturing, where there's going to be many different systems involved. So different systems for tracking materials and resources, systems tracking lab results, systems for manufacturing execution and process data. All of these are going to need to be integrated into some kind of analytic layer to be able to do the kind of trend analysis, predictions, deviation analysis that require deep investigations. All these systems are going to need to be integrated and aggregated together. And also there are often typically some kind of locked integrated platform that is not going to be very accessible other than just simply by its data outputs. And what often will show up in the process space, based on the kind of use cases we're looking at, is there's going to be very extensive work of using Excel to map across these different data outputs. There's a lot of mapping, there's a lot of translating, and there's even a lot of ambiguity. If there's not a standardized way of defining a manufacturing process, then you will often have not only different labels for different steps, but even the way those steps are broken down in different ways may not always line up with one another. And this can even be true if users are all using something like the ISA 88 standard. They might not all have the same level of granularity for the steps. So there's can be extensive work in just manually integrating these systems together, not only across scale when you were working at production versus development scale, but even at cross site where the kind of work in Excel iterates on itself, and there's just more and more time needs simply integrating these data sets together. This is really where the ontology can then be applied, is to think conceptually of a semantic layer that's going to be linked to these different data systems, where the ontologies can be used to enforce that standardization. Now, there's many different options. This is certainly not the goal to give a complete architecture. There's many options about how this could be implemented, from a relatively lightweight way where the semantic layer is kind of acting as a registry to register standardized vocabulary and standardized data models, to a more integrated approach where there's an actual mapping from the data systems into the semantic layer. But in both cases, the semantic layer would be the key place where the ontology would be applied, and the end user who wants these integrated data sets would be working through the semantic layer to have a clean, easy linked data sets and they wouldn't need to be working so hard to manually integrate and map these data sets together. And then in the particular case of our own use cases, our ontology would provide a standardized set of process definitions, vocabularies for those process steps, standardized way of aggregating the measurement data for both the process parameters, the performance indicators, and the quality attributes. These are just different aspects of measuring the manufacturing process. All of that standardization would be managed by the ontology within the semantic layer, so the user doesn't need to worry about that. All right, so I wanted to spend a little time to just take a look at a high level how we've put the ontology together. This is just a very high level view. There's of course a lot more details than going on. In the next couple of slides, I'm going to focus on a couple specific features of the ontology that I think might be interesting to this community. So we can see at the top level, we have worked with BFO. This is a BFO compliant ontology, making it easily interoperable with other BFO compliant ontologies like AFO. At the next level down, as I mentioned, we've incorporated the industrial foundry ontologies as a kind of middle level ontology. They have a pretty sophisticated array of modeling done for all sorts of manufacturing terms. So they're covering things like plans, objectives, requirements, the manufacturing process itself. This, as I mentioned, is there's quite a bit of modeling for the raw material inputs. And then at that lower level beneath that is where the CMC process comes in. And I've sort of color-coded this diagram. To think of this ontology at a big picture, we can think of it as dividing really into two aspects. On the left side, with the yellow and the orange, we have really our recipe information. This is describing what needs to be done, what kind of equipment, materials need to be used in the process? What are the different settings for the parameters and on the equipment? These are all descriptions of what we're planning to do, what our requirements are. And then these will then link to, on the right side, the purple nodes are going to be what actually happened in execution. So our actual batch process in execution, our measurement outputs that were involved. And these will then be linked to the plan on the plan and the recipe side. So then we can track which step of the manufacturing process overall we're linked to by linking it back to those plans and recipes. And we can compare our measurement values, whether they're within limits, by linking those measurements to a requirement specification for a quality attribute in this particular example. For those that are familiar with the ISA 88 standard, you'll notice many of the terms on the left side are directly drawn from that standard. So here we've directly incorporated into the ontology the different sorts of recipes defined in in that standard, from the general recipe to the site to the master, the control recipe, as well as the two different hierarchies for process steps on the process side down to the process action, which would be more of an equipment independent notion of the process steps, and then the procedure down to the phase would be an equipment dependent notion of the different process steps. All right. Now I wanted to zero in on a specific aspect of our modeling approach, because it does differ from many other ontologies. I think this may be a useful point of a complementary approach with the AFO. We have made extensive use of controlled vocabularies in this ontology. So rather than defining everything in the class or the type level, so we've often introduced general concepts that are going to describe different types of objects. This shows up in two different ways, one of which we call parameter kinds, which is a general concept that can describe something like a pH, and it will describe pH as both a measurement as well as it shows up in a recipe requirement, as well as in a process input. So if a process engineer has set the pH to be a certain level, this would be an input, or what we call a configuration. So there is no such class as a pH measurement. Here we're using in general this controlled vocabulary to, at the instance level, will describe the measurement to indicate whether it's pH or whether it's a recipe that's requiring a pH limit. And similarly for the process steps. So we don't have classes representing things like equilibrate or inoculation. These are also controlled terms that will describe many different, at the instance level, many different process stages that will also allow us to link across different types of process steps as defined in the ISA 88 hierarchy. So we can have a controlled vocabulary that will link across let's say equilibrate across the process side, which would be equipment independent, as well as the procedure side, which would be equipment dependent. And also this gives some flexibility so that different organizations don't have to agree upon the same granularity of their different process steps. They might choose to break those steps down in different ways, because none of this will be defined at the class level. That gives them some flexibility. Now, I do think that this may be an interesting point of integration with other ontologies. So other ontologies like AFO, which are very mature, have a very extensive and impressive number of classes defined in those ontologies. For example, I'm well aware that for analytic measurement data, AFO is very popular and has a very sophisticated amount of content and ways of modeling that data. If for users that are already like that approach for analytics data, but they want to extend their linked data sets to be able to link that data out to on, let's say, the recipe side or on the configuration side, rather than needing to replicate all of those classes that are already defined for different sorts of objects, like at the recipe level or at the input configuration level, they could use this vocabulary as a kind of bridge to link out from there. So I think this could be an interesting point of leverage for mature ontologies that are well defined in one area of this particular domain. Our vocabularies could be used to extend that to other domains in an easier, more lightweight method. Okay, so as a group, we've also proposed a kind of integration between the CMC process ontology and the allotrope foundation's ontology. The starting point is really coming out of the observation that the two ontologies have a lot of overlap in domains and in content, but they are intended for very different sorts of use cases. Obviously, ours is focusing on these process-oriented use cases. AFO is widely used for aggregating analytics data. Just as an example, one point of overlap we focused on quite a bit. Um, Rather than trying to kind of reinvent the wheel or trying to come up with a complicated way of integrating the two that might involve fully importing each other and coming up with a fairly complex set of guidelines, we have a proposal where there would be a kind of handoff between the two. So for users that are using AFO to aggregate their, let's say something like a time series data set, if let's say pH is being measured at a time by a sensor and it's being measured where thousands of times within a span of an hour or a day or something along those lines. From a process engineer point of view, those users typically don't need to pull all of that time series data altogether. If what they want to do is profile pH across the entire manufacturing process, they want to compare it with the limits defined in the recipe, they typically don't need the tens of thousands of measurements that might be involved by these sensors. They're typically going to look at a particular statistical value that was calculated, or they might pull a special unique measurement value, like a daily measurement value or hourly, something along those lines. So typical users on the process side are only going to be interested in a fairly small number of values that would be stored in an AFO data set. And so the proposal would be we have this kind of link where on the one hand we have this, we're tracking the sample ID between the two ontologies. That class will be represented in both, and so we would have a single instance, excuse me, that would be represented in both. That would have represented within both ontologies as a class, and then we would pull this one or multiple values that the process engineer would be interested in. It might be a statistical value that would be linked to our measurement process and ultimately link back into our general model of the manufacturing process, or it could be a particular measurement value. And so we would have these instances that are represented, they're members of a class of both ontologies, but this would be the single kind of integration point. We wouldn't have to fully integrate the linked data set or fully import them within one another. I know there's a lot more to say. I don't want to spend too much time on this, but this is an area we're very interested in bringing it to your consideration and any kind of feedback we can bring forward. Okay, and then lastly, wrapping up, I just wanted to share a couple of views of some outputs that we've created from a prototype knowledge graph to test our ontology. On the upper left, we used Anzo as a semantic platform to put together the prototype knowledge graph. On the upper left, we see a cross-scale batch run comparison. We have some data on analytic measurement data for 5 different batches at 3 different scales. We can see a simple batch dashboard that allow us to compare them. Here it's the parameters by the different working days, but this is end-to-end through the manufacturing process. And our ontology enables a pretty easy way of collecting the measurement data together. And at a single click of a few buttons, we can select the attribute we want to view and do that cross-scale analysis. And then on the bottom right, we have just a graph view of a recipe structure that's supporting the ISA 88 standard. The text might be hard to read for you, but it's really just a simple example of a monoclonal antibodies recipe, where within the graph, we have all of the relationships in the context that defines the different objects within the ISA 88 standard. So there's complete clarity over what type of recipe we're looking at, what kind of recipe components, their granularity. All of this can be enforced by the ontology, making it much easier to use the standard and have agreement on how to use the standard for different users. And that's all in there. That's where I'll wrap up. For those that want more information or to get involved, this is some key contact information. We have an email for general CMC process project inquiries. Also an email for Bertha, our project manager. She's done an excellent job. There's my contact information if you have any further questions or would like to reach out to me. But I think I'll pause there. If there's any feedback or questions, I'm certainly very interested to hear them. Thanks for your time.